Lesson 2.2 is on complex numbers, and when people first see this concept, they're kind of mind blown by it. For example, if you had your calculator and you tried taking the square root of, let's say, negative 25, your calculator would probably either say error or it would say non-real, and that's for good reason. There is not a real number times itself that would make negative 25, and you might think, well, what about negative 5? Well, negative 5 times negative 5 is 25. So for the longest time, people thought, hey, if there's a negative under the square root, you just can't do it. There is no answer. But they started to see this situation come up more and more in math, especially in the higher math classes. So they needed a way to work with negatives under the square root. And thus this complex number business was born. So way back in Unit 1, when we made our little diagram of numbers, I said, okay, we had the real numbers, and then we started breaking them down. Well, I actually lied when I said it was just real numbers. There is something opposite of real numbers, and it's what we're looking at today. They are called the imaginary numbers. So our objectives today are just to be able to work with these types of numbers, whether we're adding or subtracting, multiplying or dividing. So let's jump right in. So imaginary numbers, what they are, you know you're going to be dealing with these if you have a negative under the square root. So they needed a way to work with this, so they said, okay, if I have the square root of negative 1, we are going to say that is equal to I for imaginary. Another property that would happen is, okay, if I took that result and I squared both sides to get rid of the square root, well, the square and the square root would cancel, and we would get negative 1 equals I squared. This is going to be a simplification property that we'll use quite a bit. We'll talk about that more in just a bit. So let's practice simplifying these. So square root of negative 49, if you try typing that into the calculator, you're going to get an error. But remember that list of perfect squares that we made? I believe it was section, let's see here. Should have been section 3 in the previous unit. 49 is a perfect square, and it's 7. However, since the negative is under there, the negative comes out as I. So the square root of negative 49 is written as 7I. Okay, let's try the next one. The square root of negative 18. For now, ignore the negative and let's focus on the 18. 18 is not a perfect square, but there is a perfect square in it. If you look at your list of perfect squares, the biggest one that goes into it is 9. So I'm going to break it up into my negative 9 and 2, because 9 times 2 is 18. So the square root of 9 is 3, but it's going to be 3i because of the negative, and then I still have the square root 2. I don't care if you write your answer like that, or you can put the I at the end. Just make sure if you put the I at the end that it's not under the square root, just the 2 is. Okay, and let's look at square root of negative 80. So if we focus on the 80, 80 is not a perfect square. So I want to find the biggest perfect square that will divide into it. So if I'm looking at my list, the biggest perfect square that divides into 80 is 16. And it's 16 times 5, that makes 80. So this would become 4i square root 5. Or you can write the I at the end. So it's just like what we were doing when we were simplifying them in the last unit, except there's a negative under there which comes out as I. These are imaginary units. So now it brings us to the name of the lesson, complex numbers. Think of the word complex. They're complicated. So complex numbers contain both a real part and an imaginary part. So when you see them written, they're often written in standard form, which looks like this: a plus bi, where in this number, a represents the real portion, and the letter with the I represents the imaginary portion. Together, this entire value is a complex number. It has both a real and an imaginary part to it. So let's try simplifying. Pay attention to the operation between them. So I want to add these two complex numbers together. Very easy to do. All you're going to do is, let's do the real numbers first. So 5 plus negative 2 would be 3. And now let's do the imaginary numbers. So negative 3i plus 4i would be 1i. You don't have to write the 1. So there would be my final complex number, 3 plus I. Okay, the next one. Pay attention to the operation. I want to subtract them. So let's start with my real numbers, 10 and 14. So 10 minus 14. And now let's do the real numbers. Now be careful here. What you're going to end up doing is negative 2i minus a negative 6i. So that's really going to become plus. So I would get plus 4i. My students always struggle with making sure that this negative affects both. Got to make sure you're subtracting both. All right, now let's look at multiplying. So notice, I know I'm going to multiply because there's multiplication. When they're written right next to each other, that's multiplied. And we are going to FOIL, like what we did in an earlier unit. So first times first, 2 times 7 would be 14. Now let's do outer. So 2 times a negative 4i would be negative 8i. Now let's do inner. Negative 3i times 7, negative 21i. And finally, last times last. Negative 3i times negative 4i would be a positive 12. And when I do I times I, just like with x's, I add the exponents. So I'd get I squared. Let's combine like terms. So 14, a negative 8i minus 21i is negative 29i. And then I still have my I squared. Now there's one more thing that I would like you to do, and it goes off of what we talked about at the very beginning of the notes. If you have an I squared in the problem, I squared, we said, was equal to negative 1. So I am going to replace the I squared with a negative 1. So they multiply together. So 12 times negative 1, that would become minus 12. So notice, 12i squared became negative 12. So when you do these, if you see I squared, you think negative 1, it's going to turn the number opposite of what it was. So then the last thing is combine your like terms. 14 minus 12 would be 2, and then minus the 29i. So notice I have the real part, and I have the imaginary part. This is a complex number. Okay, let's try the next one. Let's FOIL it. First times first, 16. outer, 4 times negative 5i, negative 20i, inner, 5i times 4 is 20i, and then last, sometimes it doesn't change color here, last times last, 5i times negative 5i would be negative 25i squared. It's combined like terms, so 16, negative 20i plus 20i would cancel. And then again, we have the I squared. So we know that's going to become negative 1. And negative 1 times negative 25 would actually make it positive 25. And if I combine those, notice this one does not have an imaginary part. If you really wanted to, you could write it like this. Plus 0i. But you don't have to put the 0i. Okay, one more of these. I have the quantity 1 plus 4i squared. So what I'm going to do first, I'm going to write it twice, because that's what the squared means. And now let's FOIL it. So first times first would be 1. Outer times outer would be 4i. Inner times inner would be another 4i. And last times last, 16i squared. Combine like terms, 1 plus 8i plus 16i squared, and then remember I squared is negative 1, so it's really going to become minus 16, and then combine like terms, 1 minus 16. So my answer would be negative 15 plus 8i. All right, we have one of my favorite math terms ever. It's called a conjugate. And this is going to be how we tackle dividing. That's the only operation we haven't covered so far. So I'm going to come back to the conjugate word in just a moment. To divide two complex numbers, what we're going to do is we're actually going to turn it into a multiplication problem. So we are going to multiply the numerator and denominator by the conjugate of the denominator. And in just a moment, I'll show you why we even do this and how it's going to help with the division. So when I say conjugate, here's what I mean. If I had something in the form of a plus bi, its conjugate would be a minus bi. It's like the imaginary part changes signs. So if you saw something like negative 7 plus 5i, the conjugate would be negative 7 minus 5i. The imaginary portion changes signs. So here's how this is going to actually make the division problems easy. With dividing, your goal is to get rid of the imaginary unit in the denominator. So this first guy here, I notice in the denominator I have 4 plus I. So what I'm going to do is I am going to multiply that by its conjugate, which would be 4 minus I. Now if I multiply that to the denominator, to keep things balanced, I also have to multiply it to the numerator. And in just a moment, you'll see why this works. So I'm going to have to distribute up top. So 3i times 4, and 3i times a negative 1i would be negative 3i squared. All over, now on the bottom I'm going to have to FOIL. So first times first, outer times outer, 4 times negative I would be negative 4i. inner times inner, negative I times, or that's a positive I times 4 would be plus 4I. Sorry about that. And then careful with last times last. Positive I times negative I would be a negative I squared. So watch what happens here. Up top, I'll still have my 12I minus 3I squared. And on the bottom, my 4i's would cancel. And hopefully you've guessed it by now, there's another thing I would want you to do, and that's to get rid of the I squareds. We're going to replace the I squareds with negative 1. So 12I, that's going to become plus 3. And on the bottom, 16, it's going to become plus 1. I'm going to flip-flop the order up top. So I'd have 3 plus 12I over 17. Notice the i's have completely disappeared from the denominator. That's how you know you're doing it right. That is the whole purpose of the conjugate, why we have to use the opposite sign. Otherwise, if we don't use the opposite sign, my outer and inner will not cancel out. Picky detail. If I ask you to write it in standard form, a plus bi, then with your final answer, we have to break it apart into a real and an imaginary answer. So I would write this as 3 over 17 plus 12 over 17i. You can either put the I out back or up with the 12, it doesn't matter. So that's technically standard form, I just broke it apart. Let's try one more of these. So the next one, if I would like to perform this division, I'm going to multiply by the conjugate, 1 plus 2i. And if I do it to the bottom, I also have to do it to the top to keep things balanced. So let's FOIL. First times first, outer times outer, inner times inner, and then last times last. Be careful that we get a negative 6i squared. All over, we're going to have to FOIL again on the bottom. So first times first, 1 times 1. And then outer, 1 times 2i. And then inner, negative 2i times 1. And then last, negative 2i times 2i. Okay, now we just have to clean things up. So combine like terms, I would have 5, 10i minus 3i would be 7i. And I'm going to do the I squared step right now. I'm going to replace I squared with negative 1. So that's going to become plus 6. On the bottom, I have 1. The 2 i's cancel, which I want to happen. And then if I replace I squared with negative 1, that becomes plus 4. Combine like terms, so I would have 11 plus 7i over 5. And if I asked you to write it in standard form, my real number would be 11/5 plus, and my imaginary number would be 7/5 I. The final thing is just more simplifying because we're going to run into this in a unit coming down the road here. Write the complex numbers in standard form. So I would just like to simplify this as far as I can. What I recommend to people, mathematically, before you do anything, any kind of operations with these, simplify the negatives under the square roots first. So let's look at this first guy here. Is 3 a perfect square? And you should say no, and there are no perfect squares in it besides 1. So the only thing I can do to simplify this first guy would be to take the negative out as I. Now the back one, 12 is not a perfect square, but there is a perfect square in it. So that would break into -4 and 3, which then if I take the square root of -4, I would get 2i square root 3. And now I'm going to multiply them together. So when I multiply these together, I times 2i would be 2i squared. And square root 3 times square root 3 would be square root 9. Well, the I squared we know is -1, so that becomes -2, and square root of 9 is 3. So I get -6. Let's try the next one. Let's simplify them first. So 48 is not a perfect square, but I'd like to find the biggest perfect square in it, which is 16 and 3. So the square root of 16 would be 4, but it's going to be 4i because of the negative, and then square root 3. Now let's do the other one. 27 is not perfect, but the perfect square in it is 9. So that's going to be -9 and 3, which becomes 3i square root 3. And don't forget, there is still subtraction between them. Now remember, to add or subtract radicals, they have to be like terms, which they do happen to be. They are both square root 3's. So 4i square root 3 minus 3i square root 3 would be 1i square root 3. You don't have to write the 1. Two left. The next one, notice this entire quantity is squared. So before I do anything, I'm going to write it twice. Because that's what the squared means. Also, before I do any kind of multiplying, we need to simplify our square roots. So from the previous problem, I know that's I square root 3. And now let's FOIL them together. So first times first would be a +1. When I do outer times outer, -1 times I square root 3, well, that would just be -I square root 3. Inner times inner would also be -I square root 3. And finally, last times last. I square root 3 times I square root 3, I get I squared times square root 9. So now we're going to simplify this. I have my 1. I can combine those together because they are like terms. So if I have -1 of them and -1 of them, I have -2i square root 3. And this back guy here, let's see if we can do this at once. We know I squared is -1, and I know square root 9 is 3. So that becomes -3. So if I combine like terms, 1 minus 3, I get -2 minus 2i square root 3. Okay, the last one, just like what we were doing, let's simplify the negative under the square root first. So 50 is not a perfect square, but I'd like to find the biggest perfect square in it. And hopefully we know that that is 25 and 2. So if I simplify that, I'm going to have -25 plus 5i square root 2 all over 15. So I simplified the square root. And then the last step, and I can do this because I can do it from all three numbers. I can divide a number from all three of them. I can divide a 5. So I would get -5 plus I square root 2 over 3. And technically, if we're being picky, if I asked you to write that in standard form, we would break it apart. Here's my real number plus my imaginary number. That would technically be standard form. All right, so hopefully these imaginary numbers don't trip you out too much.